Welcome to the Superfast TouchDesigner tutorial series. In this tutorial, we are going to create a blob tracking effect using any video or composition, and we are going to combine it using a technique called time warping that allows us to control which frames we are going to render based on certain logic. As you can see in this video, we have 12 squares with the same video, but each square is rendering different sections of the video, which gives us this time warping effect that we are going to resolve. To follow this tutorial, here's what you need to know. 1. Network setup. I'll provide a screenshot of the full network. If it's too large, I'll break it into multiple images with clear indications so you can recreate it without constantly pausing the video. 2. Parameters. Instead of adjusting parameters live, I'll display them as static images, allowing you to copy them at your own pace without interruptions. Let's get started. Chapter 1. Overview. As you have noticed, the tutorials are increasing in complexity, and this one is already larger than the networks I commonly teach. So I have separated everything into sections, so you don't get lost. Let's briefly review the sections. The video input, where we will call our video, and it will be manipulated by a time warping technique. Below this, the grid pattern for time machine section, where we will see how to create this tiling animation to manipulate the video from above. In the blue section, we have the control section for the resolutions. The keyboard in to reset the blob cache if we want, these are optional. And this custom component called Finder that allows you to find any reference in the network in case you are lost. Below this is the section dedicated to creating the blobs. And to the right, we have the two sections where we extract the information from the blobs to prepare the data or coordinates to create the instances for the 3D objects or the locations of the texts. Below this, we have the blob instances, where we will create the instances based on the blob data. To the right, I have the first post-processing network. Below this, I have another network called lines instances, where we will create these lines. And following this, its own row of post-processing, which is a simple feedback. Below this, we have a single text operator, where we use the blob data to locate the text. And finally, the master composite, where we will unite all the material to make a final composition. Perfect. Let's move on with the explanation. The key concept in this network revolves around one of TouchDesigner's core principles, extracting coordinates from blob tracking to create instances or apply them a text operator. Once you grasp this technique, you'll be able to integrate it in countless ways across your projects. For now, let's focus on mastering this method. It will serve as a solid foundation for more advanced projects. To make this easier to understand, I've set up a simplified network where we'll apply instancing using the positional data from the blob track operator. As a source, I'm using two animated spheres against a solid blue background. The blob track top has two main inputs. The first is the color image, which serves as the main video source, in this case, our animated spheres. The second is the background, a reference frame that helps isolate moving elements. To freeze a reference frame from our source, I've added a cache top, which allows me to pause on a specific frame and use it as the background. This is important because without a static reference, the blob track top would have to analyze the entire image every frame, which is computationally expensive and reduces FPS. By providing a background, the operator only detects differences between the current frame and the reference, making it significantly more efficient. Before we move on, let's visualize how the blob track is detecting blobs in our video. As you can see, the operator identifies and tracks bright, high-contrast areas in real time. The detected blobs are marked with squares, representing points of interest in the image. This tracking happens because the system continuously compares the current frame with the background and detects moving elements. Now, here's my favorite part, extracting and using the tracking data. The blob track top provides all this information inside a table dat, which gives us full flexibility in how we use it. This table contains a set of useful values that help us understand and interact with the detected blobs. First, we have the UV coordinates, which represent the exact position of each blob within the frame. Next, we have width and height, which indicate the size of each detected object. And we have even more data, including the age of the blob, which tells us how long an object has been tracked. All this data allows us to generate instances, whether it's text, shapes, or any other interactive elements, based on the real-time motion of the blobs. Here, I'm using the blob data in two different ways. First, each blob generates an instance at its coordinates. To demonstrate, I've used a simple diamond shape. Second, I'm using the blob ID to create text labels, which are displayed in red to make them stand out. At first glance, this might look simple, but the real challenge comes next. Synchronizing the blob data with instances so they stay perfectly aligned in real time. That's what we'll tackle in the next step. Now, let's apply blob tracking data to create 3D instances. To do this, we need to process the blob tracking data using a series of chop operators that will allow us to manage and manipulate the information effectively. The first step is to convert the tracking data from a table dat into chop channels. To do this, we use a dat to chop operator. Simply drag the table data into the date to chop. Let's review this network for instancing. In this simplified setup, I have a select chop pulling data from the dat to chop, along with 2 additional select chops extracting specific values. One extracts U and width for the x-axis position and blob width, while the other extracts V and height for the y-axis position and blob height. To handle aspect ratio adjustments, I've added math chops. Right now, we're working in a 1:1 aspect ratio, a perfect square, so no correction is needed. However, when dealing with non-square resolutions, adjusting the aspect ratio becomes crucial. In this case, each math operator applies a multiply operation to account for these differences. Finally, all data is merged here, and a rename operator is added to label the channels properly, making it easier to use them as position coordinates. Let's set up instancing in the geometry comp. Opening the geometry comp VM, you'll see that the blob tracking coordinates are mapped to X and Y. Normally, the first time you do this, it can be quite difficult to find the instances in the camera viewport. This is usually due to the scale settings you're using, as well as the camera settings. Let me show you. I'll select a camera without adjusting any settings. As you can see, the diamond instances are scattered everywhere, except where we want them to be. That's because the camera isn't set up the way we need it to be. To do this, we switch the projection type to orthographic and set the ortho origin to bottom left. The ortho width should remain at 1, while the near value is set to 0.1 and the window size to 1. These values ensure that the camera matches the workspace aspect ratio, preventing instances from being stretched, misaligned, or cut off when resizing the canvas. If you modify the ortho width or window size, you'll notice distortions in the instance placement. This happens because the blob track top outputs normalized UV coordinates, where 0U and 0V is at the bottom left and 1U and 1V is at the top right. Using a perspective camera would distort these coordinates, but switching to an orthographic projection removes depth, ensuring a 1-1-1 mapping between blob positions and instances. Before moving forward, we must understand aspect ratio calculations, because if we don't adjust for aspect ratio, the positions of our instances will distort when switching between landscape, portrait, or custom resolutions. The aspect ratio of a screen or composition is the relationship between its width and height, expressed as a fraction or ratio. For example, a standard 16.9 resolution, 1920x1080, has an aspect ratio of 16.9, meaning for every 16 horizontal units, there are 9 vertical units. Then, in blob tracking, the output coordinates are normalized UV values. These values are independent of pixel dimensions, but their proportions change if the screen aspect ratio changes. When working with any resolution other than a perfect square, the y-axis needs to be scaled to maintain the correct proportions. For example, let's switch our composition to a 16.9 aspect ratio. First, you'll notice that the instances have shifted and no longer align with the blobs. This happens because we need to apply a calculation to the height to correct this issue. The simplest formula to do this is dividing height by width that will give us this number, 0.5625. Now we can use this value to change the V coordinate and height by multiplying it by 0.5625 in the second math chop. This compresses the vertical space accordingly, ensuring that instances maintain the correct proportions. Now, if we switch to another well-known aspect ratio in portrait mode, such as 9:16, we follow the same calculation and apply it in the same way to the V coordinate and height. For example, let's change the resolution to 1080 according to 1920. We already know that dividing height by width gives us 1.777. By using this value in the math chop, we correct the aspect ratio issue, ensuring the instances remain properly aligned. You can also map these values from the constant, so the calculation happens automatically whenever you choose any resolution. Here, I'm dividing the height by the width, just as we did manually. Value. Now that we've aligned the instances, let's see how to position text using blob tracking data. In top operators like the text top, we use absolute pixel coordinates instead of UV values. So if our resolution is 1080 x 1080, the X and Y positions range from 0 to 1080. That means if we want something right in the center, we set X equals 540 pixels and Y equals 540 pixels. Unlike UV coordinates, which always stay proportional, absolute positioning depends on the screen size. So let me explain this next network, which will allow us to convert the relative UV coordinates into absolute XY coordinates. You can also use this as a template for future projects. Here I have created 3 select operators to separate the values I need. In this case, the first one selects the ID, the second one selects the U coordinate, and the third one selects the V coordinate. We leave the ID as it is. I added a null just for symmetry, but it's not necessary. The second and third select operators have a math operator connected, which we simply use to multiply the input value by the resolution we need. This approach makes handling aspect ratios much easier because we only need to multiply the values by the desired resolution. Since we are working in a horizontal layout, we multiply the U coordinate by the width and the V coordinate by the height. Finally, we use a merge operator to store all the values in a single operator. With rename, it's important to use specific names, text, X, and Y, because these are the ones that the text operator will look for. Finally, we convert this into a table and drag it into the specification DAT option. This ensures that the text appears in the same positions as the blobs. Now that everything is well explained, let's create the network for our project. A quick pause. If it's your first time on the channel, hi. I'm Okamarufu, and I share your obsession with learning TouchDesigner. I love this program, and I do my best to share everything I know to make learning easier for you. If you want to go even deeper, you can join nearly 3,000 people on my Patreon, where you'll get access to all my free VJ packs, complete project files, and exclusive components and plugins. I've also set up a fully organized shop with conceptual VJ packs, advanced plugins, and a lot more. Everything is neatly arranged in collections, so you can easily find exactly what you need. And if subscribing isn't your thing, no worries. You can still grab individual project files anytime, no strings attached. So if you're ready to take your visuals to the next level, create better projects, and support what I do, check out my Patreon. Now, to understand how time warping works, let's review the following context. There are 2 operators with which you have to familiarize yourself now: the texture 3D and time machine operators. Essentially, the text 3D operator stores a sequence of images as a 3D pixel array. In simpler terms, the texture 3D captures a specified number of frames using its internal cache, transforming them into an image array. These frames can then be individually selected and displayed using other operators. It's commonly used in conjunction with the time machine, which leverages this 3D texture to pinpoint specific video frames. But how does it work? The time machine allows us to select previously stored frames based on the color of a source image, which we typically limit to a grayscale range. Let's illustrate this with a practical example. Here, I've created a mini network to better illustrate this concept. First, we configure the texture 3D to store 60 frames and disable its continuous update, ensuring it captures only one instance of the frames. This is ideal for demonstrating the effect. By clicking Pre-fill, we can recapture the latest 60 frames again. The time machine setup is straightforward. We specify the total number of frames, which in this case is -60. This tells the time machine that black corresponds to the first stored frame and white corresponds to the 60th frame. Now, the magic happens with the second operator connected to the time machine's input. For this, I have a constant top connected, which allows for easy color selection. By adjusting the values between white and black, we are going to access each of the frames saved in the texture 3D operator. You'll observe on the right video that each intermediate value corresponds to a specific frame from 0 to 60. The time machine essentially selects which frame to play based on the chosen color between white and black. So far, quite simple, right? In summary, to understand this better, activate the viewer of the texture 3D. Right-click on the viewer and activate the option Display Pixel Values. Now you will see here in white text the information that interests us according to the position of the mouse inside the viewer. The most important thing is the Z coordinate, which will express the number of the frame to which each of these thumbnails corresponds. To verify how this works, position the mouse on this thumbnail in the corner. You will see that the value of Z is equal to 0, which tells us that this thumbnail corresponds to the first frame. If we move the mouse to the right, we can see the sequence of frames as it advances in numerical order. Here we see frame 1, frame 2, frame 4, until we reach frame number 7. And if we go to the last square, we can see frame 59. With this, we can verify that indeed, if the constant is in black color, it will show us frame number 0 in the time machine. And if the constant is in the middle, for example, it will show us the frame that is more or less around here. It should be approximately between frame 29 and 31. Perfect. Now in our example, the interesting thing is that we do not have a single square, but a grid of 3 by 4 squares that are animated in sequence. Let's see the example below. As you see here, each rectangle, according to the tone of grays that it has, is calling a part of a different frame assigned to the color space that each rectangle occupies. With this, we achieve this fascinating effect of temporal warping, where we can play by calling different parts of the video. Now then, how did I create this animation of patterns? Let's review the network up here to explain it to you. The two most important operators here are the grid SOP and the ramp. The logic is quite simple since we will use instances. For this, you already know that we need a GEO component, and we will use the grid to create the coordinates, where we are going to duplicate this rectangle from here several times. First, the grid is set to 3 by 4. This will give us a total of 12 instances. Second, the ramp is set with a resolution of 12 by 12. This will give me 12 values to manipulate the animation later. I will not explain this in much detail because there is already a lot of information about instances in my previous tutorials. But basically, in the GEO component, I am referencing the grid and using the X and Y coordinates as they correspond. And in the second tab of instances, I am referencing the ramp in the color mode section, but we cannot reference the ramp as it is. For this, we have to create a sequence of nodes to prepare the data and efficiently convert them into instances. For this, create a top to chop to convert the texture of the ramp into channels. After this, we use a shuffle with the sequence channels by name option, where we unify the channels with the data we need so that it works in the instances. This last shuffle is what we reference in the color instances, and we select the colors as they correspond, RGB, and even the alpha channel. Basically, each column of this shuffle represents a specific RGB value that gives us the color that will modify the instances. If we want to understand this better, we can go to the ramp and select View as Points. Here we can see each of the points that brings with it color information, which is the information we use to create the sequence of colors using the instances of the GEO component. In summary, we are dividing the ramp into 12 segments, represented as points, where each point has the color information corresponding to the space it occupies, and this information is sequentially applied to the instances. Here, I've simply created another ramp vertically to have a second ramp, and mixed it using a composite to achieve a different result. This result is then connected to a switch, allowing me to control the type of animation I have. One is a more sequential animation, and the other gives us something more random. Both are used to manipulate the time machine we have up here. I've also created a select top here that calls the final result of the render top with the animation we just reviewed. Now that everything is well explained, let's create the network for our project. It's understandable that many individuals encountering TouchDesigner tutorials for the first time might feel overwhelmed. The platform can present a significant learning curve, and the sheer volume of information and intricate details can lead to frustration when attempting to follow along or develop personal projects. To address this, I'm developing a series of online courses that offer flexible access and allow you to learn at your own pace. The goal is to establish a robust understanding of TouchDesigner fundamentals, making future tutorials, projects, and continued learning significantly more accessible. If you're looking for a structured and comprehensive entry point, I encourage you to explore my TouchDesigner school. Currently, you'll find a highly effective beginner class designed to tackle these initial challenges directly. For those interested, the link is provided in the description. Chapter 2, Network. Remember, I'll now show you a screenshot of the network so you can copy it. Depending on its complexity, it might take more than one screenshot, and I'll include clear indications whenever necessary. Chapter 3, Parameters. Alright, I'm going to explain how this network works, while we review the parameters, references, and other aspects of the network that best match the results we want to achieve. First, the most important thing. Let's see all the parameter references, which in reality are not many. but these dotted lines with the arrows make everything seem completely chaotic and quite difficult to understand. But for that, we use the Finder, this custom component that you can find for free on my Patreon. Let's see the list of references we have. First, let's refresh the operator, and now unfold the menu. The first item is the constant. This is referenced to the fit, which is here basically so that any video that enters through this input is automatically fitted to the resolution I am using. On the other hand, you can use much higher resolutions, but since I am recording my screen, I lowered it dramatically so that the program runs better. After that, the same resolution is referenced to these math operators. Remember, at the beginning we did it to calculate the aspect ratio. And finally, the resolution is referenced to all the render tops we have, which are 3 in total. Perfect. The next is the text 3D of this section, which is basically referencing the cache value directly in the time machine. For this, you just drag this value inside the time machine and multiply by -1 to obtain the negative number. Very well. Now the last one is the keyboard in, which is referenced to the cache. I have it like this because, depending on how you want the blobs to behave, you can choose to freeze the frame or play the video with a delay. This way, the blob tracking will read the blobs in reference to the last frames or in reference to a frozen frame. For now, I am going to leave it active because I want to see the blobs that do not stay in the same place but rather follow the movements of the dancer. That's regarding references. Now, you already know this entire sequence, so we are not going to explain it again, so I am going to skip to 2 important sections. How to create these lines that connect each of the blobs. Now let's see how we create the lines, which I have called instances because in some way each line belongs to the location of a blob. But in reality we are not using instances. So we can say that they have a behavior that resembles them, but are not exactly repetitions of a geometry, as instances are. In this case, we are drawing the coordinates of a continuous line where we are giving the information of each point to a chop to draw them based on the UV coordinates of the blobs. To do this, I have created 2 select operators here, and in each one I have consecutively called math 2 and math 3, which have the information of the UV coordinates of the blobs. In the first select, I have only limited myself to selecting the U coordinate, and in the second select, the V coordinate. I have connected both to a merge to have all the values in one place. Remember, now the only thing we have are the UV coordinates of the blobs. And finally, the last step is to create a chop2, which will be in charge of reading this data and creating a graph. Here the important configurations are in channel scope and attribute scope. In the first, we choose which channels we want to read and what attributes each channel will have. You can choose several attributes, but the ones that matter to us are point position X and point position Y. With this, we are indicating to the chop to that each coordinate is a point, and it will be in charge of drawing continuous lines between each point. Make sure the mapping option has one sample to each point selected. Finally, I've connected this to a GEO and created a material called line, which, as its name indicates, allows me to texture geometric lines more efficiently. Here we can manipulate the colors of the line and other aspects of its general appearance. In the general setup, we can even change the thickness of the lines if we are interested. Remember, here you can play and explore different possibilities. Below these instances, we have the text top, where we have referenced the final value of the network that has the logic to create the texts that we saw in the previous section. Here we have not changed anything, but remember that you can still select the font of the text, the size, the colors, etc. Here in the post-processing lines section, I have simply created a feedback network that is already quite well known. The first select is referencing the result of this render top to keep things organized. And at the end of this sequence, the add operator is referenced within the feedback, as you already know. If you have doubts about this, I recommend watching the complete video about feedback that I have on my channel. Perfect. Up to here, the most important thing is resolved. Now let's see how we use the blobs in the form of rectangles to complete these compositions. The first select that I have here is calling the final result of the render top that shows me each square of the blobs in the correct coordinates. To this select, I have connected 2 operators. The first is edge, which, as its name indicates, will only recognize the edges and leave out the fill. With this, we manage to obtain only the outline of the rectangles. This works with any shape and is quite faithful when it comes to separating the fill from the edge. Here's where I can choose what color I want the rectangles to have. The second operator, blur, is connected to a composite that, in turn, is connected to the original video signal that I have referenced within this select. Here, what I want is to use the multiply blending mode so that we use the blobs as masks, and thus we can recall pieces of the video to mix them further ahead. Finally, I have another select with the original video plus the result of the blobs that we have here. Using the screen blending mode in the composite, we have a kind of transparency of the blobs over the original image. Up to here, it's extremely simple. Remember to use these resources to create other possibilities. For example, you could use a remap to rearrange the pixels of an image in new coordinates based on the blobs. The last network where I do the final composite is a series of select operators. Each one I have renamed with the material they are referencing. From top to bottom, we have the lines, which I have chosen to make black. After that, the text, which is in red. Followed by this, the rectangular blobs. And all of this will be superimposed on the last video mix, where we have the original video plus the mix we did between the blur and the multiply to have a different color in the rectangles, where the blobs are visualized. All of this works using a composite with the over operation. And finally, I reference this to my final output called select. In case anyone wonders why I use so many selects and not so many nulls, and why at the end I have put a select instead of an out, it is for two reasons. The first is that the selects help me avoid a lot of cable crossings and connections, and they also consume almost no resources. The other is that the select at the end allows me to drag any part of the network and visualize it on the big screen without having to take major steps. And the out should really be used if you already have a case where this will be in a performance, context, exhibition, or you want to convert this into a custom component or other things where it is pertinent to use it. For now, since TouchDesigner allows you to use the views option and see any operator, it is not strictly necessary to use an out. Alright, the result of all this is as follows. We have a video as input, and we can use any other video at the beginning of the network. Thanks to the 3D texture and the time machine, this video is played back at different times based on the instance grid. After this, we send the signal from this video to Blob Tracking to obtain blobs, which we later convert into UV coordinates using data manipulation. This allows us to locate and obtain lines, rectangles, or different effects based on the blobs. The logic is quite simple, and the rest involves compositing techniques or post-processing where we mix the signal to our liking. I hope you've successfully completed this tutorial. If you have any questions, feel free to ask in the comments or join the discussion.